Alright, so today I'm going to be explaining and walking through a Diels-Alder retrosynthesis, and we are given the final product and we need to deduce the starting materials. And so we're going to start by analyzing exactly what occurs during a Diels-Alder reaction, and we'll make cuts to figure out where our two starting materials that we're trying to find came together to form this product. And so we know that in a Diels-Alder reaction, a new pi bond is formed right here, and two new sigma bonds are formed here and here. And so these sigma bonds kind of split the product in two, and so what I like to do is draw an arrow this way and an arrow this way to separate the two. And that's going to help us deduce our two starting materials. And so we know one of these starting materials is going to be our diene in a typical Diels-Alder reaction, and our other starting material is going to be our dienophile. And our diene is going to be represented by what's to the left, represented by the left arrow in our final product. And our dienophile is going to be represented by what is to the right with the right arrow. And so that kind of helps me keep them separate. And we know that our diene, by virtue of having more electron density, is going to be our nucleophile. We know that our dienophile is going to be the electrophile. Alright, and so now let's start with the diene. We know, by virtue of this having a bridgehead, that our diene is going to be some type of ring. But first thing we need to do is figure out how many carbons are in this ring. And we can do this by numbering the carbons here. So we know that the bridgehead is part of the diene ring, and so this is carbon 1, 2, 3, 4, 5, and 6. And so this is going to be our diene, and so now we know that our diene is a 6-membered ring. And by virtue of this being a Diels-Alder reaction, I'm not going to go through the exact mechanism and where all the electrons go, but our diene is going to have a pair of double bonds right here, one of which will form our new double bond on that side. And so now we know that this is our diene that we're starting with, and we know that in our reaction we don't need heat because by virtue of it being a ring, it's locked in S-cis conformation. Which is required in order for Diels-Alder to occur, but if it were not locked in a ring, then you would need heat to keep it in that conformation. So, now that we have our diene, let's move on to the dienophile, which is everything to the right. And so, let's see what's going to make up that. And so, we see that in this reaction, or in this product, we have a double bond right here. And so, in order for this double bond to be here, that means our dienophile must have started as a triple bond. Because that contributes to forming one of these sigma bonds, one of these new sigma bonds that we cut to separate our product into two initial starting materials. And so we will start with the triple bond in our dienophile, and then we see that we have a methyl group coming off this side, and a carbonyl coming off this side. Notice that when we draw this, it has to be 180 degrees because of the geometry of a triple bond. And we will have let's see, up here, we have our carbonyl. We have two more carbons coming off like that. And so now we can see that if we were to start with these two starting materials and undergo Diels-Alder reaction, the nucleophile would attack the electrophile, and they would combine. This would come up to form the bridgehead. As you can see, I'll label these carbons to mirror them. And there we go. I feel like that's a fairly easy, consistent, repeatable way to break down the product of a Diels-Alder reaction and separate it into its two starting materials.